Hello, everybody. This is Ilka Hermes from Park Systems Europe. I would like to thank you for having me at the Nanoscientific Symposium Asia. Today, I am going to talk about PFM, or piezoresponse force microscopy, and in particular about how we can stabilize the piezo response when we do resonance-enhanced PFM. And we can do that by doing frequency tracking, and that allows us a higher accuracy and lower crosstalk for thin film characterization. We can achieve this frequency tracking by coupling our research AFM tools. So here I'm showing the NX10, the NX20, NX HiVac, and the NX12 with an external log-in amplifier from Zurich Instruments. So I want to start off by talking about ferroelectric materials. So if we look at ferroelectric materials, what we find is certain areas where we have a uniform, parallel electrical polarization, and these areas are called ferroelectric domains. However, the overall distribution of these domains is pretty random, and that is giving us macroscopic electrical polarization that is zero. But what makes these materials interesting for application is that once we apply an electric field, we can actually switch the domains in the direction that we want by choosing the electric field direction. And we can not only do this like macroscopically by applying an electric field to the overall material, but we can also do that like to target like a certain domain area in some sort by applying like a microscopic electric field. For example, by using an AFM tip to apply a DC voltage and thereby switch the domain orientation only in this particular area below the AFM tip. And that allows us to somehow customize the domain patterns to the application that we need. And what is also required for the application then of these materials is that the switch domain orientation is then stable even as after we remove the electric field that we applied externally. And these customized domain patterns are applied, for example, in nonlinear optics. Here, the materials that are used is typically lithium niobate or lithium tantalate. And here we actually have a PFM phase image of such a periodically polarized lithium niobate, or PPLN. And we can nicely see this periodic pattern in the PFM domain, right? So we see a bright contrast, dark contrast, and this very ordered, which kind of means that here we have one domain that is oriented in one direction, and then we have this other domain, and dark is oriented in the opposite direction. Now, the writing of the domains can also be used for memory devices. So basically, memory devices can, for example, use as active layer ferroelectric material, and then we can store our information by switching the domains like we want. And here, a material that is used is often barium titanate. If we want to now characterize ferroelectrics, we can make use of the fact that all ferroelectrics are also piezoelectric. And in particular, for PFM, we use the inverse piezoelectric effect, which means as we apply a voltage to the material, we can either see an extension or a contraction of the material, depending on the field direction and the orientation of the electric polarization in the material. In PFM, we do the electric field application on the nanoscale, which means we apply the electric field that induces the mechanical deformation of the material with a nanometer-sized AFM tip. And to do this, we use a conductive cantilever. So we have some sort of metallic coating, and the cantilever scans with the tip in contact with the sample. So we always are in contact with the sample. And as we scan over the surface, we apply an AC voltage. And this AC voltage, due to the inverse piezoelectric effect, introduces a periodic oscillation of the material, which is also called the piezo response. We can see this here in red. And then this sample oscillation or piezoresponse is detected by the beam deflection and then detected here on the photodiode. The sample signals we get is for once the phase of this piezoresponse as compared to the excitation signal. And the phase is giving us information on the domain orientation. And then we also have the amplitude of the piezoresponse, which carries information on the position of domain walls. So whenever we reach a domain wall, the amplitude of the piezoresponse gets minimal. Now there's different approaches to perform PFM. And the main distinguishing factor here would be the frequency that we choose for the AC excitation. And one important parameter or value here is the contact resonance of the cantilever. So when we think of a cantilever swinging, we usually think of a free resonance where we have only one side fixed of the cantilever. But in contact resonance, we basically look at some sort of standing wave motion of the cantilever, because now both sides of the cantilever is fixed. One is fixed to the chip, and the other one is the tip is in contact with the sample. The contact resonance is typically 3 to 5 times higher than the free resonance of your cantilever. And what is important to keep in mind is that the contact resonance is very sensitive to tip sample contact mechanics. And I'm going to show you on the next slide how much that actually matters. If we now look on this very simplified schematic of a frequency spectra of a cantilever in contact with a sample, we can see here at higher frequencies the contact resonance, or CR. And now the first approach to do PFM would be to choose the AC excitation far away from the contact resonance. And that actually gives us less crosstalk, because now we're not that sensitive to tip sample contact mechanics. So this does not require, basically we do not expect so much crosstalk when we do this very far away from the contact resonance. However, if we have materials that have a very low inherent piezoresponse, for example, thin films, the signal is not going to be very strong. So we do not have any enhancement of the signal. The second approach to do PFM would then be, for such samples that have a very low inherent piezoresponse, is to choose an AC excitation that is very close to the contact resonance and already uses the enhancement of the contact resonance. So that is going to increase the signal to noise ratio on our PFM signal, but at the same time, now we are now basically the stability of our signal also depends on the stability of the tip sample contact, because that basically gives the frequency of the contact resonance. Now, one way around this dependence on the tip sample contact mechanics is to track the contact resonance. So even if our tip sample contact mechanics change and thereby the contact resonance changes, we now can just add an additional frequency feedback, and this frequency feedback kind of corrects for the shift in the contact resonance. So I wanted to show you how much the contact resonance is actually affected by the tip sample contact mechanics. So I just choose a sample and use the same cantilever and measured the contact resonance at different positions of the sample. So we have, for example, here at position A, we get a contact resonance of 358 kilohertz. Then we move the cantilever onto a different position on the same sample, and we get a contact resonance of 349 kilohertz. Then we move to a third position, position C, and we get a contact resonance of 357 kilohertz. That means over the same sample with the same cantilever, we see a shift of the contact resonance of almost 10 kilohertz, which basically when we would have chosen a single frequency without frequency tracking, for example, at 355 kilohertz, and then we move to position B, we would end up with a complete phase inversion of the PFM signal. And that would, of course, make our interpretation of the data very difficult, because we don't know that this phase conversion? Is it inversion? Is it now actually a different domain, or is it only topographic crosstalk that influences the tip sample contact mechanics and thereby the contact frequency? Yeah, so I hope I could show you how much this contact resonance depends on the tip sample contact mechanics. So one way around this is to track the contact resonance by doing dual frequency resonance tracking, or DFRT. So here, when we look at our contact resonance and we apply the AC excitation at the contact resonance, we at the same time also generate two sidebands, left and right of the contact resonance. And basically, now that the contact resonance shifts, for example, to lower frequency, the amplitude ratio of these two sidebands is changing. And now the frequency feedback that we have in DFRT compares the amplitude ratio of these two sidebands and then adjusts the AC excitation accordingly to keep this amplitude ratio of the two sidebands constant at the initial value where we set the feedback up, right? So now the AC excitation shifts back onto the contact resonance and the amplitude ratio of the two sideband is constant. If we look at the results that we can generate for once with the frequency tracking and once without the frequency tracking, so both of these measurements are now resonance enhanced, but one, the DFRT measurement in the upper row tracks the contact resonance. We can already see that here in the upper row, this is the topography of a BFO sample, bismuth ferrite sample, pretty rough surface. We see the topography for both measurements look very similar, but then if we look at the PFM signals here on the side, we see a lot less topography crosstalk. So all these holes that we see down here where we do not do frequency tracking, we cannot really recognize here in the PFM amplitude and the PFM phase when we do DFRT. This gets particularly obvious once we draw a line profile across one of those features in the topography. So I highlighted this here with a blue box. We can see the dip in the topography here in both scans. Now, when we look at the PFM amplitude and PFM phase in DFRT, we only see a very weak crosstalk in the PFM amplitude, and we do not see any crosstalk whatsoever in the PFM phase. We only see this nice 180-degree phase contrast that gives us the orientation of the domain. And in the PFM amplitude, we only see these nice amplitude minima at the position of the domain walls. Now, in the single frequency resonance enhanced PFM measurement without frequency tracking, we see this topography feature very clearly in the PFM amplitude and also in the PFM phase. So the PFM phase gives us a nice 180-degree phase contrast for the domain itself, but then when we look at the topography feature, this is almost a phase contrast of 100-degree. So it would be easy to confuse this with the real physical information on the ferroelectric domain on this material. Furthermore, if we look at the DFRT feedback output, we have an additional measurement channel, that gives us information on where the contact resonance now actually shifts. In this case, the DFRT feedback or the frequency channel only gives us basically the topography information. So we see a frequency change whenever there is a topographic feature. But the idea is that possibly for materials that have inhomogeneous nanomechanical behavior, we can use the DFRT feedback signal as an additional measurement channel. So another advantage of this DFRT PFM is that we can do vertical and lateral PFM measurements at the same time. So shown here is the vertical contact resonance on the same sample, the BFO sample, and the vertical contact resonance is at 350 kilohertz. The lateral contact resonance is at 690 kilohertz. Now, for both of these resonances, we can generate our two sidebands, left and right, and have two different feedbacks running, one for the vertical contact resonance and one for the lateral contact resonance. And thereby we can generate, here we see again the topography on the same measurement area. Here we see the vertical amplitude that we've seen before. And now at the same time, we could also measure the lateral PFM amplitude also with the frequency tracking, and we see that there is a very distinct difference in the vertical and the lateral signal, where we now see basically in-plane domains on the sample. So I hope I could show you that DFRT gives you accurate and also topography crosstalk-free PFM imaging in the vertical and in the lateral. Now looking at a more applied sample system, we could look at ferroelectric photovoltaics or photoferroelectrics. And the idea is that these could give you a simplification of the regular photovoltaic device. So as we know, photovoltaic devices require a certain asymmetry to effectively separate charge carriers from each other. So basically now we have our conduction band and valence band in a semiconductor that is the active layer in the photovoltaic. We basically need to overcome the Coulomb forces that hold these two particles together, and then separate them in different direction on the device, right? So the electron needs to be extracted on one side and the hole needs to be extracted on the other side. And typically this is achieved by matching several different layers together or introducing a different doping profile for the layers. But the idea is that in ferroelectrics, you can achieve this asymmetry in the energetic levels just by using the electric polarization of the material itself and basically introducing a bulk photovoltaic effect where you already have the asymmetry in the energy profile. So if we look at the electrostatic potential, the idea is that once you absorb some light and you excite your charge carrier, basically your electron can only, in this electrostatic environment, it can only be extracted along one direction. And thereby you do not need to have like different layers or different doping profiles. Plus, what has been observed is that some ferroelectrics, for example, BFO, have photoconductive domain walls. So what these researchers did is they did a PFM scan on a BFO sample, and then they shined some light onto the sample and measured the photocurrent with CAFM. And they found that this photocurrent image corresponds very nicely to the PFM scans. And that is particularly obvious if we take a line profile across the photocurrent and the PFM amplitude at the same position. So we have the photocurrent in red and the amplitude in blue. And we find that wherever there is a domain wall, we also get a maximum in the photocurrent. Now, a system where ferroelectricity has been discussed a lot is perovskite solar cells. And the question here is the active layer of perovskite solar cells ferroelectric? And would this thereby qualify as a photoferroelectric material? The active layer is methyl ammonium lead iodide. And this material has certain phase transitions that just symmetry rise would allow for ferroelectricity as well as ferroelasticity, which is more of a mechanical effect instead of an electrical effect. And indeed, PFM measurements on this domain have revealed some domains. So we can see here, this would be the topography, and then here is a PFM scan. That there are some domains in the PFM that we do not see in the topography. So there are some domains, but the question is, are these domains actual ferroelectric domains, or are they introduced just by mechanical differences of the sample? So basically, is it mechanical crosstalk? So here we can of course use our DFRT measurement to find out if this is actual mechanical crosstalk or is this a real ferroelectric system. signal. So here we see the topography on a large methylammonium lead iodide crystal. So we get a very flat topography. But then when we look at the PFM amplitude and the PFM phase, we can here, where we do not have any topographic feature, we can nicely see the outlines of such a triangular domain, and the same in the PFM phase. If we look at a line profile of the PFM phase, we see that there is a phase contrast of 170 degrees, very close to the full 180 degrees. So one might think that this is actually a ferroelectric domain. But then when we look at the frequency signal of our DFRT scan, we can see the same domain also in the frequency channel. And what this means when we draw a line profile across this here, we see actually that the contact resonance changes by 20 kilohertz as we go across this domain. So there is a significant change of the contact resonance once we are on this domain. And this actually leads to our conclusion that there is definitely a very strong mechanical interaction and a very strong mechanical crosstalk in the PFM measurements. So at least part of the contrast that we observe in the PFM comes from a change of the contact resonance that is very likely introduced by ferroelasticity, so a mechanical behavior of the material. This does not completely exclude ferroelectricity, but we have to keep in mind that there is a mechanical influence on our PFM signal when we measure on these materials. So to conclude, I hope I could show you that dual frequency resonance tracking, or DFRT, significantly reduces the topography crosstalk for your PFM measurements when you do resonance enhanced PFM imaging. There is the possibility to do simultaneous vertical and lateral PFM measurements, so you get more information on your sample in just one scan. And at the same time, frequency channel of the DFRT can carry additional information that is going to help you characterize also to get more information on your sample and on the mechanical information of your sample. And with this, I'm at the end of my talk, and thank you for your attention.